Hello ladies and gentlemen, we're going to talk about modulus, the complex conjugate and division of complex numbers in this very interesting session. So let's make a start. First of all, let's talk about the modulus of a complex number. Okay, we've got an example here. We've got the number 4 plus 3i. That's the position on the Argand diagram. The x coordinate or x length here is 4. The y length there is 3, okay? The modulus of z, written this way with these vertical lines either side of the symbol z, is nothing more than the distance of z from the origin. So it would be the length of this little red line here, ladies and gentlemen, okay? It's the length of the line from the origin to z. Just repeating myself, there it is. If you can work out the length of that line, you've got the modulus, no problem. So if z was x plus iy in general terms, then the modulus of z by Pythagoras' theorem, looking at this little triangle we've just made over here, would of course be the square root of x squared plus y squared, wouldn't it? Good old Pythagoras to the rescue again. And if z equaled 4 plus 3i, then the modulus of z would simply be the square root of 4 squared plus 3 squared, which, as we know, is 5. Okay, how about that? Now, here's some properties of the modulus. So we've got the modulus of z1 times z2. That means you multiply them together and then find the modulus is equal to the modulus of z1 times the modulus of z2. Now, that's not intuitively that obvious, but if you pick any two examples of complex numbers, just anything you like, and you put that to the test, you'll find it works just fine. Take it from me, I've done it. And similarly, for division, we know that the modulus of z1 having been divided by z2, then take the modulus, is equal to the modulus of z1 individually divided by the modulus of z2 individually. That's also not all that intuitively obvious, but it does work when you do it. Okay? This one here is definitely not that obvious until I show you a diagram in a minute. So add z1 and z2 up and then take the modulus. That is going to be less than or equal to the individual modulus or moduli of z1 and z2 added up. Okay? Moduli is the plural because it's a Latin word, by the way. Now, this little diagram will show you why that's the case. We've got z1 here and we've got z2 to here. Now, this here, this blue line z1 plus z2 is the result of adding z1 and z2 together. Alright? Now you can see that this blue line would be less than the individual lengths of this one and this one, wouldn't it? Of course it would. And it would only be equal to the sum of those two lengths if those numbers z1 and z2 were in alignment. In other words, collinear along the same straight line. In that case, you would have this would equal that plus that. You think about that. It's perfectly logical what I just said there. Okay, here comes the complex conjugate, a very important little animal which we need to know him very well for reasons which I'll explain in a moment. So first of all, let's just define the thing. If z is equal to a plus bi, for example, then the complex conjugate is called z bar. Z bar, okay? Z bar. And z bar, ladies and gentlemen, is a minus bi, which is simply the same as this, except that the sign in the middle is changed, okay? It's reversed. That's how it works. So we reverse the sign of the imaginary part in z to obtain z bar. That's what we do. For example, if z was 4 plus 2i, then z bar would be 4 minus 2i. Now that's pretty easy, isn't it? Here comes the geometrical significance of the complex conjugate. Now, have a look at this. This is 4 plus 2i, and there we've got 4 minus 2i. That is the complex conjugate of this little beastie here. If this was z, this would be z bar. Yes, okay. So you can see just by this simple little illustration here that the complex conjugate is in fact the mirror image of the complex number z about the x-axis. That's how it works, guys and gals. Okay, so if z was 3i, here's another example. If z was 3i, let's just mark that in. Z bar would be minus 3i. There they are marked in there. Okay, z was 3i. You see, it's the mirror image again about the x-axis, yeah? We'll do another one now. If z was minus 3 minus 2i, then z bar would be minus 3 plus 2i. Let's just plot them in there. Here is Mr. Z, and Mr. Z bar is going to be there. You can see that they're mirror images of each other about the x-axis, can't you?